This is the lecture on sanitation and resource recovery. So today's agenda is to identify useful resources and materials that can be covered from sewage and fecal sludge, to calculate the dimensions of a dry waterless toilet and determine how long it can be used until it needs to be emptied or replaced, and to design a composting reactor by determining the mixing of different organic materials to achieve a target ratio of carbon to nitrogen. So let's start out with the composition of domestic sewage. So domestic sewage refers to wastewater that goes down the drain from households. Right, so you have urine and feces, which are part of wastewater, and together those are referred to as excreta. You also have water that's used for flushing, and this all gets mixed together, of course, and goes down the drainage pipes. In addition, in some cultures, anal cleansing water is used, and so that water may be in addition to or instead of flush water if it's a dry toilet. And in some cultures, dry anal cleansing materials are used, like toilet paper. And so those materials may also be disposed of in the toilet or flushed down the toilet. Collectively, all of these materials, with the exception of urine, are usually referred to as brown water. So this would be the case of a toilet where urine is collected separately. And if all of it is collected together in the same toilet, then this would refer to as black water. And this is usually in the United States, large cities that have flush toilets and sanitary sewer systems. The toilet water would be consistent with black water. However, in the United States, it's also very common to mix together with black water all drainage water from the household, like from showers and baths, from kitchen sinks and dishwashing, from bathroom sinks, and from washing laundry, and any other drains that may appear in the house. So collectively, all of these drainage water sources are referred to as gray water. And gray water, it's important to distinguish gray water from black water because the two sources of wastewater are very different. Gray water is much higher much lower in contaminants typically than black water, and it's also much higher in volume. But in some places, these two are collected together, like in the case of San Diego and most of the United States, and we would refer to this as domestic sewage. Now, how else can we conceptualize domestic sewage? Well, urine can be seen as a resource. It contains very high concentrations of nutrients and relatively low quantity of pathogens. So these can be seen as a resource for producing sustainable fertilizers. Feces, on the other hand, is the nasty stuff. This is what contains all the pathogens and material that can be infectious and make someone sick. However, it's also very high in organic matter. And if properly treated and digested, it can be converted into biogas or digested to produce an organic matter that can be used as soil amendment or another type of fertilizer. Now, water for flushing is reclaimable. That water starts off as very clean water and then can be treated and reused. And any other organics in the system can be considered as fuel. They're combustible, they're paper or biomass that can be burned and used to produce energy. Now, gray water, on the other hand, can be more easily treated, especially if it's collected separately from black water. So usually we think of sewage as how to deal with it or how to treat it and dispose of it. But the new paradigm for wastewater management is to really view wastewater and to view sewage as resources, nutrients, energy, and water that can be reclaimed and reused. And it also brings up the question, why do we mix all this stuff together anyway? Because if it's easier to treat when it's separately collected, then perhaps there can be alternative designs to manage wastewater in a household that can be more sustainable and can separate out some of these cleaner waste waters that can be more easily treated and reused on site. So in raw sewage or domestic wastewater, to summarize, the volume composition is approximately 99.9% water and 0.1% other stuff. So that's a lot of water used to convey a very small amount of waste on a mass basis or a volume basis. So just to put it in perspective, if we have a population of 10,000 people, this population would typically produce 1.5 to 2 million gallons of sewage per day, which is a very large volume that needs to be handled and treated at a treatment facility. So what are these pollutants that comprise the 0.1%? We have debris and grit, like rags, little pieces of plastic, sand, gravel that end up getting down the drain, usually from washing items in the household. You got particulate organic matter, including fecal matter, food wastes, toilet paper. You've got colloidal and dissolved organic matter. These are fine particles that are more difficult to remove and separate from the water. You've got dissolved inorganic material like nitrogen, phosphorus, nutrients, and other nutrients from waste and also coming from detergents. You've got pesticides, potentially heavy metals, toxic compounds, depending on the use and the zone that's producing the wastewater. In industrialized nations, typically the volume of wastewater, domestic sewage produced, is about 25,000 to 100,000 liters per person per year. And most of that is gray water, very small percentage being urine, and an even smaller percentage being feces. So nitrogen, on the other hand, you can see 85% of that is present in the urine. 60% of all phosphorus is present in the urine, 54% of all potassium. So urine comprises a very small volume of the wastewater, but it has a very large percentage of mass of all the nutrients that you would find in wastewater. Therefore, if we can separate out urine and treat it and manage it separately from the rest of the waste, it's possible to be able to recover these nutrients to produce more sustainable fertilizers. Organics are found in gray water, but they're also almost half of the organics are found in feces. And most of the water, as you can see, is found in the gray water. So if we can separate out gray water from urine, from feces, and manage these waste streams separately, we can more easily recover energy, nutrients, and clean water from these resources. You can also see that gray water and feces are high in pathogen concentrations, but urine is relatively free of pathogens, with the exception of a few specific diseases in some tropical countries that are excreted in the urine, and also with the exception of cross-contamination from fecal matter. So given what was presented in the previous slides, I want you to take a minute, you can pause the video if you'd like to, and think of 3 useful materials that can be recovered from sewage or wastewater. And think of how these materials can be safely recovered. And how can we prevent the risk from pathogens that are found in sewage? And then finally, what are some technologies or techniques that can be used? And feel free to be creative here. Maybe something that you've seen before, maybe something that you haven't seen, but you just thought of. What are some techniques that we can use to recover resources from sewage? All right, so as I mentioned, if you grew up in an urban area or in the United States, with the exception of some rural areas and small towns, many mid-sized and large cities in the US are serviced by centralized sanitary sewer. So, if you live in a city in the US, most likely your wastewater gets collected into a pipe that conveys that wastewater to a centralized pipe in the street, and that wastewater is conveyed over to a treatment plant, which might look something like this, where aeration and settling processes are used to biologically treat the wastewater and produce cleaner effluent that can be further treated or discharged for reuse. Right, so this is the typical centralized sewer system, and there are, however, many households that are not connected to centralized sewer system and instead utilize decentralized wastewater treatment or decentralized sanitation technologies. Now, furthermore, globally, there's 1 billion people who don't have a safely managed or an improved sanitation facility, and therefore they rely on practicing open defecation in order to take care of their needs. Furthermore, there's 0.7 billion people globally who utilize shared toilet facilities. So they don't have a toilet in their household and they have to rely on shared toilets. In addition, there's another 0.7 billion people globally who utilize toilets in the household that are inadequately functioning. So they're either collapsing, they're overflowing, they're not designed properly, they're not safely managed. But if we look at the overall sanitation service chain, in order for someone to have safely managed sanitation, they need to have all components of this entire chain. So not just the toilet at the household, not just the pipes under the ground, but the entire system from start to finish. So that starts with the user interface, which is the toilet structure. It continues with on-site containment, collection, storage, or treatment. So I already gave the example of piped sewer systems where sewer pipes convey the waste away from the households and to a centralized treatment plant. However, many households utilize septic systems or some variety of a pour flush toilet, where the waste from the toilet goes into a septic tank. Sometimes gray water also goes into the septic tank as well. And from that septic tank, it would be discharged into a leach field where the liquid portion would percolate into the ground, and the solids over time, when they build up, they would be removed often by a tanker truck or some manual sludge removal operations and conveyed over to a centralized treatment facility. After treatment, the treated effluent can be reused for irrigation, or the treated biosolids can be reused for agriculture or other uses. So in order to have the entire safely managed sanitation service chain, all of these pieces need to be in place. So let's look at some variations in what you might see around the world in terms of user interface. Right, so you have flush toilets, which are common in the United States. You also have pour flush toilets, which are very common throughout the world. You've got dry toilets where the toilet is an opening that opens into a pit and there is no flush water. It's just contained and maybe covered when it's not in use. And you've got a variety of different slabs and either squat versus sit style toilets that are used throughout the world. For on-site containment, collection, and storage, so you can have a variety of systems here too, like seen here in this photo below, double vault system, where the waste from the toilet is conveyed. This looks like it would be for a pour flush toilet, so it'd be conveyed after pouring some flush water into the system into one of these pits. That pit would fill up over time where the solids would accumulate. The liquid would percolate into the ground. When one pit is full, it can be covered and then left to sit and digest for some period of time, during which time the other pit can be used in operation. After a storage period, the contents of the first pit can be removed, disposed of properly and safely, and then when this pit fills up, you can reuse the first pit again. In other systems, when the pit fills up, you may just excavate a completely new pit. In some systems, urine is collected separately from feces, and there are a variety of different designs of pits and pour flush pits, dry pits, systems like this one, which are elevated, and the excreta is collected in a chamber that is enclosed in concrete. So you have a wide variety of different styles of toilets when it comes to on-site containment, collection, and storage. In terms of conveyance, for on-site systems, one of the methods of conveyance is using a vacuum truck, like you can see here. However, you will also find places in the world where wastewater or fecal sludge, for that matter, is conveyed using other means like motorcycles or manually, or using containers. In some densely populated urban communities, simplified sewerage systems are constructed as well. These sewers would connect mostly only the black water and convey that to a centralized location, whereas gray water may be discharged to a different drainage system. For the treatment, you also see a wide variety of technologies, right? Different types of reactors, some that are designed for handling solids like fecal sludge, others that are designed for handling liquids like wastewater, where there's a higher volume of water and less concentration of solids. You've got constructed wetland systems, drying beds, a wide variety of different approaches that can be used to treat waste that's removed from the on-site tank, or wastewater that's conveyed through a series of pipes. And we're not going to get into any more detail on the different treatment technologies because that's beyond the scope of what we cover in this particular course. However, we will do an example on the design of some on-site sanitation facilities like a latrine. So let's look at the approach that can be used to size a latrine. Right, so in sizing latrines, we use the volumetric fecal sludge accumulation rate, which is typically between 0.02 and 0.09 cubic meters per person per year. However, it depends on the pit's proximity to the water table. It depends on the diet of the users and the type of anal cleansing materials that are used or other materials that may be disposed of inside the pit, which may cause it to fill up faster or fill up slower, depending on people's habits. General rule is that when a pit is 80% full, it should be covered, its use should be discontinued, and a new pit should be excavated, or the old pit should be emptied so that it can be used again. In terms of ventilation, the superstructure that goes above the pit can be properly ventilated by orienting the vent pipe, the slab, and the shelter with respect to the prevailing wind direction, or by installing HVAC system to provide ventilation mechanically. The air exchange rate is calculated as the ventilation rate, or the cubic meters of air per hour passing through the superstructure, divided by the volume of the superstructure in cubic meters, for example. And an air exchange rate of 8 hours to the -1 is the recommended value. So if you are looking to determine the necessary ventilation rate for a pit latrine, and you know the volume of the superstructure, and you know the minimum air exchange rate that is required, which is 8, then you can use this equation to calculate the ventilation rate that will provide that air exchange rate of 8 hours to the -1. All right, so let's do an example problem. We're going to design a shared pit latrine for an emergency shelter with dimensions of 1 meter wide by 1.25 meters long. So the question is, how many meters deep must the pit be excavated in order to accommodate 20 households of 5 people per household for at least 1 year, assuming an accumulation rate of 0.04 cubic meters per person per year, and ensuring that the pit will not reach more than 80% capacity after 1 year. Okay, so we'll start by calculating the volume after 1 year. And so that's equal to 0.04, the accumulation rate, cubic meters per person per year, multiplied by 20 household times 5 people per household, which is 100 people, multiplied by 1 year. And so that gives us a value of 4 cubic meters. So that's the volume that will accumulate in the latrine after 1 year. Next step is to determine the depth requirement, assuming our dimensions of 1 meter by 1.25 meters. So the depth is the only dimension that's unknown. The length and the width are given. So to get the depth, we take the volume, 4 cubic meters that we just calculated in the first step, and we divide that by 1 meter multiplied by 1.25 meters. This gives us a value of 3.2 meters. So that would be the depth of sludge accumulated in a 1 by 1.25 meter cross-section over a period of 1 year. However, in order to make sure that the pit does not reach more than 80% capacity after 1 year, we would have to divide it by 80%, which would give us a value of 4 meters. So therefore, in order to design a shared pit latrine for 20 households that will last for at least 1 year, the depth would need to be 4 meters. So the next step would be to determine, is it actually feasible to excavate a pit that has that depth? Otherwise, you might need to make a decision that if the depth needs to be half as much, perhaps it can only accommodate 10 households of 5 people per household for a year. Or perhaps it can only accommodate 20 households of 5 people, but only for 6 months. Another type of sanitation facility that is used in some places in the world, which is waterless and is a form of on-site sanitation, is the composting toilet. It's also known as the eco-san latrine. This is a good solution in some areas that may have high water tables. Instead of using water, a desiccant is added after each use, such as sawdust or ash. And this helps with drying out the material inside the toilet, and also in some cases may also help with the composting process. Typically, a double vault system would be used with urine diversion. So when one of the vaults fills up, it would be capped off and the other vault would start to be used while the first vault is composting. So urine is diverted separately from the feces. This helps keep the compost material dry and facilitates the also easy recovery of nutrients from the urine, as mentioned previously. So composting toilets were first designed and developed by a priest in England, and they became very popular in the 1970s and the 1980s in Nordic countries, where it has since been commercialized. However, it's important to note that when this technology is transferred to some other regions of the world, such as tropical regions where there are different diseases that circulate in the population due to the climate, it can cause unintended consequences. For example, soil-transmitted helminths are intestinal parasites that thrive in tropical climates, especially where there's low sanitation coverage and where people are exposed to the soil that may be contaminated with waste. So if composting toilets are used in tropical climates and the compost is then used as a soil amendment, which might put it into exposure for, put humans at exposure for contracting new helminth infections. And so where one technology may be common and popular and appropriate for northern countries like Norway, Sweden, Finland, that same technology may be inappropriate for some other countries. And it's important to design a toilet system and a sanitation facility according to the local needs and the local climate. So in order for all pathogens to effectively die off in a pit latrine, you need to achieve a combination of temperature and holding time, which can range from minutes to days to weeks to months to even years, depending on the pathogen type. So some pathogens, like bacterial pathogens, might die off more quickly than other pathogens like parasites, which can last for years at ambient temperatures. So this graph here just shows the relationship between temperature and time when it comes to pathogen die-off. And so zone A here indicates the region where at least 99.9% reduction is achieved. Zone B would be the region where at least 90% reduction is achieved for all microbial groups. And zone C indicates time temperature combinations that have variable reductions. So it could be less than 90% for some microbial groups, could be more than 99.9% for others. Really just depends on the pathogen. So if you really wanted to be in the safe zone here, zone A, you need to achieve higher temperatures. This can be done with composting, but only when the compost pile is turned over regularly and you achieve that high temperature due to the microbial activity. So in many cases in practice, the temperatures reached inside the compost pile do not get as high as 50 degrees Celsius. The other important part about designing composting facilities, and this is true whether you're talking about a latrine or a toilet, or whether you're talking about a compost facility for food waste. But the ideal ratio of carbon to nitrogen in the compost pile needs to be 30 on a dry mass basis. So what does that mean? It means if we have something like human waste, like feces, we need to mix that with other materials, because the carbon to nitrogen ratio of human feces tends to be between 6 and 10, which is too low for the ideal ratio that we need for composting. So therefore, we need to add another material that has high mass of carbon and a relatively low mass of nitrogen. Something like wheat, straw, hay, grass clippings. Actually, grass clippings would be considered more of a green waste. Their ratio of carbon to nitrogen is lower than 30. We would need to add something like sawdust or straw or hay, which has a much higher carbon to nitrogen ratio. So let's do an example problem for composting toilet. So let's assume that fecal material is 6.3% nitrogen on a dry mass basis and has a carbon to nitrogen ratio of 10. And let's assume that sawdust is going to be the co-composting material that we use, and it has a nitrogen concentration of 0.1% with a carbon to nitrogen ratio of 400. So the first question, what is the dry mass of nitrogen in 1 kilogram of feces? And the second part, what is the dry mass of carbon in 1 kilogram of feces? Finally, how much sawdust needs to be added to each kilogram of feces on a dry mass basis to achieve a carbon to nitrogen ratio of 30. All right, so to approach this problem, we're going to start by calculating the mass of nitrogen on a dry mass basis in 1 kilogram dry mass of feces. All right, so we do that by multiplying 0.063, which is 6.3%, multiplying that by 1 kilogram, which gives us 0.063 kilograms of nitrogen. We then calculate the mass of carbon by multiplying that nitrogen mass by the carbon to nitrogen ratio of 10. So that means 10 kilograms of carbon per 1 kilogram of nitrogen, which gives us a value of 0.63 kilograms. Next step is to set up the equation where we are aiming to achieve our carbon to nitrogen ratio of 30. So we know that we have 0.63 kilograms of carbon, and if we're assuming that we're normalizing this to 1 kilogram of feces, we know that we have 0.63 kilograms of carbon. We don't know yet how much mass of carbon from sawdust will be contributed. So we're going to leave that as a variable. We do, however, know that we have 0.063 kilograms of nitrogen, but we don't yet know how much nitrogen is going to be added from the sawdust. So we're going to leave that as a variable. So we can set this equation up to solve for the mass of nitrogen in the sawdust. Or sorry, this is the total mass of the sawdust. Using the same series of calculations that were performed here above for the fecal matter. So the total mass of the sawdust multiplied by the percent nitrogen multiplied by the ratio of carbon to nitrogen, 400, will give us the mass of carbon in the sawdust. Right, so that's the total mass of the sawdust, shown here, multiplied by 0.001, multiplied by 400. On the denominator here, we can take the total mass of the sawdust here, multiplied by 0.001, and that's going to give us the mass of nitrogen in the sawdust. So then we can take this equation, 30 is equal to 0.63 plus the mass of sawdust times 0.001 times 400, divided by 0.063 plus the mass of sawdust times 0.001, and we can solve it for the total mass of sawdust here. And this N here is a mistake. It should just say the mass of the sawdust, the total mass, not the mass of nitrogen or carbon. Right, so if we rearrange this equation here and we solve for the mass of the sawdust, we find that it's equal to 3.405 kilograms. So therefore, for every kilogram of fecal material, we would need to add 3.405 kilograms of sawdust in order to get that 30-to-1 carbon to nitrogen ratio, which is ideal for composting. However, in addition to sawdust, we would also need to add some type of bulky material like corn husks or another bulky composting material that would provide some aeration for the pile. Otherwise, it could go anaerobic, and that would not help us out in terms of achieving composting, which requires an aerobic environment. So either it needs to be turned over frequently, or we would need to add some type of bulking agent like hay, for example,